feel like you're taking advantage of him.
Whatever. He's working off his rent. Let's go, Tube Sock. Hit me!
So this video we want to discuss the idea of electrostatics. It's more commonly known as static electricity. It's probably how you've described it before and used it, where you might, walk across the floor in the wintertime in your socks and touch a doorknob and get shocked. Maybe when you get out of the car and touch the door handle, once you get out you get shocked. That's the static electricity effect. We refer to this as electrostatics. It's the behavior of stationary charged particles, because the term electricity actually means moving electric charges and the term static means not moving. So electrostatics is more appropriate to refer to the stationary charged particles. All matter, as you know, is composed of atoms, and those atoms are composed of charged particles within the atom itself. That's where all of our basic electric charge will come from. The nucleus of an atom contains protons, which are positive, and neutrons, which are neutral, hence the name neutrons. Surrounding the nucleus is what we call the electron cloud. That's where we know that the electrons are located. The electrons are negatively charged. And so this is our basic underlying structure of everything in nature, and our electric charges, right, our positives and negatives, actually come from the actual atom itself, the protons and the electrons. So the protons are tightly held in the nucleus and are much more difficult to move. The electrons are very small, about 2,000 times less massive than the proton, and they're located out around the actual nucleus, so they're much easier to move around. So when we talk about electrostatics, we talk about the charges that we might build up in one place or another, or how the charges move from one to another in a spark or a lightning. We're generally talking about the movement of electrons. It's not that larger particles can't move, it's not that protons can't be moved, it's just that typically it's the electrons that really are doing the moving when we talk about charges. There are two types of electric charge. I already mentioned them before, and you're probably familiar with them. We have positive and negative. These terms came about simply because of the labels that they had on things when they were studying the idea of electricity. They had positive and negative, simply opposite of each other, and those names and those identifying terms basically stuck. But electric charge itself is really a fundamental property of matter, just like inertia we've talked about is a fundamental property of matter due to the mass of an object. Electric charge is what causes then an electric field, and therefore also causes objects, those charges, to experience a force in that electric field. Very similar to the idea of a mass and a gravitational field. So you know that you have a mass and another mass, and they will attract each other through a gravitational force that we've discussed before. But there's a field that reaches out beyond the objects, so they don't have to be in direct contact. Similarly, there's an electric field around electric charges, and then any other electric charges into those electric fields or near those electric fields will be affected. You know the old saying there that likes repel and opposites attract. This applies for electric charges. So you have the two positive charges are going to push each other away, the two negative charges would push each other away, but any positive and negative charges specifically would then attract each other in that behavior. So you're familiar with that, and that's how we basically are able to observe, study, and discover the whole idea of electric charges and how they behave. We can identify the different charges as positive and negative, but we also need to be able to measure how much charge we have in science. The unit we use for that is a coulomb. In order to have a coulomb worth of charge, we need about 6.25 times 10 to the 18th electrons. If we have that many electrons, we're going to have a negative 1 coulomb worth of charge. Now looking at that number is just huge. It's basically 625 with 16 zeros following it. If you want to see about how big that is, just actually write that out on your paper. That's a huge number of electrons. The electron and the proton, it turns out, actually have the same magnitude of charge. Even though the proton's 2,000 times more massive than the electron, they still have the same amount of charge. So if you wanted to have a positive 1 coulomb worth of charge, you would essentially need what's equivalent to 6.25 times 10 to the 18th protons to get that amount of charge. Now, you might have come across already in some of your science classes the fact that atoms are neutral. They have the same amount of protons as they have electrons. And since they each carry the exact same amount of charge, those charges cancel each other out equally. So the diagram here just shows essentially 6 positive charges, 6 protons in the nucleus, and 6 electrons in the electron cloud surrounding that. So as a result is you have an electrically neutral atom. This is a very common behavior that's observed in nature, and that pretty much everything we come across is electrically neutral. Many chemical reactions and behaviors and things that take place in nature are based on this basic idea here, and result in this idea that everything in nature behaves towards being electrically neutral.
Mr. Hill, there's something wrong with Scooter.
Don't worry about it. I kept the receipt.
Oops! Someone forgot to boost!
Mr. Hill, there's something wrong with Scooter. You saved Scooter! Yeah!
Minute Maid enhanced with a natural energy boost. Put good in, get good out.